In our last class meeting, we started on section 1.7, relations. And the first thing we did was the definition of relation, definition 1.36. Definition of relation: a relation or a binary relation on a non-empty set A is a non-empty set R of ordered pairs. In other words, it's a set of ordered pairs x, y of elements x and y of A. So once again, a relation which is really a binary relation. And this is on page 55. You can copy these definitions in your notebook, the theorems, the postulates, all of those should be in your notebook. The examples should be in your notebook. On a non-empty set A. It's a relation on a non-empty set A. And that relation is a set that we call R of ordered pairs. X, Y. So that's your old definition of a relation, set of ordered pairs, any set of ordered pairs of elements X and Y. So that's what we have for our definition there. As indicated on page 55, that is, a relation is a subset of the Cartesian product A cross A. If the pair AB is in the relation, is in R, we write A relation B. That's how we write it. A relation B. So that means that the pair AB are in set A. So A relation B, we have an element of B, the element of A, set A, relation of another element of set A. And the relation, once again, is a set of ordered pairs that you get. And say that A has the relation R to B. A has a relation R with B. That's what we're saying. So some relation that A has with B, and that relation can really be anything. If AB, the ordered pair AB, is not a member of R, if that ordered pair is not a member of the set of ordered pairs X, Y, we write A relation with the line through it means that A does not have the relation with B. So once again, if AB, that AB is not in the relation, we write A is not a relation with B, and A does not have a relation with B. If that order pair is not in there. This notation agrees with the customary notation for relations, such as A equals B, and A is less than B. what you think of the equality relation and the less than relation. The relation, if you have A equal B, the relation is equality. Okay, if you have A less than B, the relation is less than B is less than. This is the relation of this. All right, we have an example there. You want to take a look at that? Okay, example 1 on page 55. Let A be the set -2, -5, 2, 5, and R be the relation, the set of ordered pairs 5, -2, 5, 2, -5, -2, -5, 2. Then R relation 2, -5 relation 2, 5 relation -2, and -5 relation -2. But 2 is not relation 5 because there's no ordered pair 2, 5. So 2 is not relation 5, 5 is not relation 5. There's no ordered pair coming from that set of numbers. As is frequently the case, this relation can be described by a simple rule. X relation Y if and only if the absolute value of X is the same as y squared plus 1. That is, absolute value of X equals y squared plus 1. So you can see that because because of the X's and Y's, you can graph those and see what kind of graph you have, and you can get the equation of that graph. And you can see that that indeed is the equation that you would have there. If you were to, so as we said, both X and Y come from A. They come from the same set. So you have your set A, so X and Y come from that same set. That's why you're just pairing basically the elements of that set with the elements of that set. You have 4 elements in that set. But these are some of the ones that you would have. You can have that relation there. That relation doesn't include everything that you can see there because you can have other ordered pairs there. But that would be a relation for that set. But as far as the equation is concerned, you can graph those ordered pairs of numbers and see what the graph looks like. You have 5, -2, 1, 2, 3, 4, 5, 1, 2, -2. Okay, you have 5, 2, 1, 2, 3, 4, 5, 1, 2. All right. Let's see, where else do you have? You have -5, -2, 1, 2, 3, 4, 5, -2. All right. And you have -5, 2. 1, 2, 3, 4, 5, 2. So those are some of the points that you have there as far as those numbers are concerned. So you can look at those points and you can see that if you take the absolute value of X, you will get y squared plus 1. Now, if you look at your ordered pairs, you have 5, -2. So if you have 5 or -2, that means x equals what? What, x equals 5, y equals -2. And if you try to put that into that formula, you'll see that it works. Absolute value of x equals y squared plus 1. So if you put the x in here, that would be 5, absolute value of 5 equals y is -2, you would have -2 squared, and then plus 1, absolute value of 5 is 5, -2 squared is 4, 4 plus 1 is 5. So the formula that they have there checks out, and that's what you would have as far as that formula is concerned, and that would really define the relation between those variables. Any mapping from A to A is an example of a relation, but not all relations are mappings. This is, any mapping would be a relation, but not all relations are mappings. Because for a mapping, you have to have something that's being mapped into something. An example illustrates. We have 5, 2, a member of R, and 5, -2, a member of R. Both of those are members of the relation that just showed you above there. And for a mapping from A to A, the second element Y is the ordered pair. In the ordered pair 5, Y would have to be unique. You see? So if you look at what you have there, 5 is the first element. You don't have any second element, 2 second elements of 2, but you have the second element of 2, or second element of -2, which is different, they're unique. Our main concern is with relations that have additional special properties. More precisely, we are interested for the most part in equivalence relations. That's what we're interested in. And as you mentioned there, these have additional special properties. They don't just have the properties that we mentioned above, just in a set of ordered pairs, but they have additional properties. So the next thing we want is the definition of equivalence relation. Equivalence relation. So based on what we have there, we can do more ordered pairs to see exactly what happens. It looks like something like that. Something like that. This is a vertical line. Okay, that definition on page 55, definition 1.3.7, definition of equivalence relation. A relation is, it says a relation R. The relation R on a non-empty set A is an equivalence relation if the following conditions are satisfied for arbitrary x, y, z, and a, satisfied for arbitrary elements of a, these conditions are satisfied, then we have an equivalence relation. Now, this is a general definition, abstract definition of an equivalence relation. Equality is an example of an equivalence relation. So we want to keep that in mind, that this is a general, the relation does not have to be equality for it to be an equivalence relation. That's what we're saying here. This definition. Okay, there are three properties that have to be obeyed for an equivalence relation. If R is an equivalence relation, X relation X. It's like equality, we say X equals X. And this is for all X a member of A. For all X a member of A. X relation X. If it's equality, it would be X equals X. If it's some other relation, abstract relation that we don't even know what it is, it would be X relation X. If you have X relation X, then that satisfies the first property, which, as you know, is reflexive. When you think about equality, you just put this over here for a reference. Equality is an equivalence relation. You say two things are equal. So this would be like X equals A. The relation is equal to. That's the relation. This is the relation is equal to. So yes, X equals that's reflexive. So these properties, if you think about equality and express these properties in terms of equality, that can give you a previous foundation that has already laid these properties. So next, if X relation Y, then Y relation X. And that is symmetric property. For equality, you would have if X equals Y, then Y equals X. That's what we call the symmetric property. And the symmetric property of equality is equals, but equivalence relation, you can have an abstract relation that can be an equivalence relation. It doesn't have to be equality. So that's what we're saying in abstract algebra. Things are more abstract. You don't really know what the relation is, but you know that there is a relation. So for the next one, if X relation Y and Y relation Z, then X relation Z. And that is the transitive property. For equality, we would say if, which is an equivalent relation, we would say if x equals y and y equals z, then x equals z. That's what we would say there for equality. Well, once again, keep in mind that it doesn't have to be equality. The equivalence relations might have to be equality. All right, let's go on to the next page. All right, next page. We have so there. Example one, we were able to write the order pairs. We were able to state what things, terms, or numbers that do not relation together according to the relation that we have there. And also, we came up with a formula for the relation. Now, if we go on to example two. For example two on page 56, the relations are defined on the set of integers. Okay, so we have a relation R and it's defined on the set of integers, which we represent by Z. And it's defined by X relation Y, if and only if, IFF for short, the absolute value of X is equal to the absolute value of Y. That's what we have. So that really equation there really defines the relation that we have between the numbers. All right, so now we want to know, is this reflexive? Is it symmetric? Is it transitive? That's the question. We want to use arbitrary values x, y, z, and x, y, little z, and the integer big Z. All right, so we have the relation, and the relation is defined by that equation there. The question is, number one, is R, you just say R to the same relation. Okay, is the relation, let's say both, is the relation R reflexive? You want to know if it's reflexive. Now, if it's reflexive, X, the relation X. If it's reflexive, X is relation X. So, X relation Y, if and only if absolute value of X equals the absolute value of Y. So, in this case, we will be saying that the absolute value of X equals the absolute value of X. You see, because this is X and Y. And we have absolute value of X equals the absolute value of Y, because this defines the relation. And the question is the absolute value of X equal to the absolute value of X? And the answer is yes. So this will give you, if you simplify this, you get X equals X. X equals X. So that means that the relation is reflexive. Yes, R is reflexive. You see. Okay, next thing you want to know is the relation that we define, is that relation uh, symmetric between the two? Is the relation R symmetric? Now, for symmetry, we're asking, is uh, X relation Y equal to Y relation X? That's what we have for symmetry, because the symmetry in general, we said if X relation Y and Y relation X, X relation Y and Y relation X, X relation Y, then Y relation X. So we do each one. Okay, we do X relation Y. Okay, X relation Y. We have absolute value of X equals absolute value of Y. So we have for the first part, and we're saying if this is true, does that mean that Y relation X is true? That means Y relation X. So we can see that this is true. Okay, good. So you can see you have that relation X. So, well, the easiest way to do this is to start out with X relation Y, and then so that you end up with Y relation X. So we have X relation Y, and that implies that absolute value of X equals absolute value of Y. And of course, that implies, because we do have real equality here, that implies absolute value of Y equals absolute value of X, which implies that Y relation X. So we get a logical conclusion from X relation Y. So yes, it is symmetric. Okay, the last one is sensitivity. And for this, you have two things that have to be true. All right, X relation Y and Y relation Z. So both of those things have to be true. And this implies both of these imply that X value of X equals absolute value of Y and absolute value of Y equals absolute value of X. So now the absolute value of X equals absolute value of Y. Absolute value of Y equals absolute value of Z. So now we just have regular equality. So based on equality, if X equals Y and Y equals Z, then based on equality, that means X equals Z. So we have the absolute value of X equals Z. Then we say, hey, according to our relation, this is X relation Z. So we'll just write it as what it is according to our relation, which is X relation Z. So that shows that X relation Z follows the direct result of the X relation Y and Y relation Z. All right, example 3. The relation R defined on the set of integers by X relation X if and only if X is greater than Y. It's not an equivalence relation. So you want to determine, is this an equivalence relation? So you determine whether or not the three properties are met: the reflexive property, the symmetric property, and the transitive property. If those three properties are not met, then it's not an equivalence relation. So we have X is not greater than X for all X in number of Z. That's number 1. For number 2, we have X is greater than Y implies, does not imply that Y is greater than X. Note the R is transitive. Well, that means the relation is transitive. And last but not least, transitive, X is greater than Y and Y is greater than Z implies that X is greater than Z. The following example is a special case of an equivalence relation on the integers that will be extremely important in later work. Example 4. The relation congruence modulo 4 is defined on the set of integers as follows. X is congruent to Y modulo 4 if and only if X minus Y is a multiple of 4. We write X equals y mod 4. And shorthand for x, x is identical to y mod 4. And shorthand for x is congruent to y modulo 4. Thus, x is congruent to y modulo 4 if and only if x minus y equals 4k for some integer k. We demonstrate that this is an equivalence relation for arbitrary x, y, and z in big Z. So for number 1, x is identical to x modulo 4 since x minus x is equal to 4 times 0. X is identical to y modulo 4 implies that x minus y equals 4k, or for some k a number of z, which implies that y minus x is equal to 4 times negative k, and negative k is a number of z, and that implies that y is identical to x modulo 4. Number 3, x is identical to y modulo 4, and y is identical to z modulo 4. That implies that x minus y equals 4k, y minus z equals 4m, for some m and k a number of z. This further implies that x minus z and x minus y plus y minus z is equal to 4 times k plus m. And k plus m is a member of z, which implies that x is identical to z modulo 4. Thus, congruence modulo 4 has the reflexive, symmetric, and transitive properties and is an equivalence relation on z on the set of integers. Okay, not only do we have equivalence relations, but we have equivalence classes. On page 57, we have the definition of equivalence class, definition 1.38. So we have definition open too long. Okay. Definition 1.38, definition of equivalence class. All right, the definition states that let R be an equivalence relation on the non-empty set A. For each little a member of big A, the set A equals a set of all x, a member of A, such that X relation A is called the equivalence class containing A. So all X and A such that X relation A. Once again, normal definition, let R be an equivalence relation on a non-empty set A. For each A related member big A, the set square bracket A equals a set of all x. So remember A such that x relation A. So once again, that is called the equivalence clause containing A. Equivalent containing A. So that's what this called. Okay, we have an example. The relation in example 2 defined on Z by X, relation Y, is equivalent to the absolute value of X equals the absolute value of Y, is an equivalence relation. The equivalence class containing 0 is square bracket 0 equals the set whose only element is 0. Since 0 is the only element X, a member of Z, such that the absolute value of X equals 0. Some other equivalence classes are given by the equivalence class of 1 would be 1, negative 1. The equivalence class of 3 would be negative 3, 3. For A not equal 0, the equivalence class of A is given by negative A. Okay. The equivalence class of A is equal to set negative A equals to equivalence class. Since A and negative A are the only elements in Z with absolute value equal to the absolute value of A. Example 6. The relation congruent modulo 4 was shown in example 4 to be an equivalence relation. Since X is identical to Y modulo 4, if and only X minus Y is a multiple of 4. The equivalence class consists of all those integers that differ from A by a multiple of 4. Thus, the equivalence class of 0 consists of all multiples of 4. Similarly, the other equivalence classes are given by negative 7, negative 7, negative 3, 1, 5, 9, negative 6, negative 2, 2, 6, 10, and the equivalent class of 3 would be negative 5, negative 1, 3, 6, 1. That's what you have there. In both example 5 and 6, the equivalence class separates the set Z into mutually disjoint non-empty subsets. Recall from section 1.1 that the separation of elements of a non-empty set A into mutually disjoint non-empty subsets is called a partition of A. It is not difficult to show that if R is an equivalence relation on A, then the distinct equivalence classes of R form a partition of A. Conversely, if a partition of A is given, then we can find an equivalence relation R on A that has the given subset as its equivalence classes. We simply define R by X relation Y if and only if X and Y are in the same subset. Proof of these statements are requested in the exercises in this section. The discussion in the last paragraph illustrates a situation where we are dealing with a collection of sets about which very little is explicit. For example, the collection may be finite or it may be infinite. In such situations, it is sometimes desirable to use the notational convenience known as indexing. We assume that the set is the collection, the sets in the collection are labeled or indexed by a set curly L of symbols lambda. That is, a typical set in the collection is denoted by a symbol such as big A sub lambda, and the index lambda takes on values from the set curly L. For such a collection, A sub A, set A sub A, we write union sub lambda is a member of curly L, big A sub lambda. For the union of the collection of sets, and we write the intersection lambda is a member of curly L big A sub lambda for the intersection. That is the union of A sub lambda, lambda a member of curly L equals the set of all x such that x is a member of A sub lambda for at least one lambda member of curly L. And for the intersection, you have the intersection lambda is a member of curly L of A sub lambda equals the set of all x such that x is a member of A sub lambda for every lambda a member of curly L. If the indexing set curly L is given by curly L equals 1, 2, n, then the union of the collection of sets, set A sub I, might be written in any of the following three ways. The union could be written as A sub 1 union A sub 2 union A sub n. It could be written as union I is a member of curly L A sub I, and that equals the union A is going from 1 to n. Okay, the index notation is useful in describing a partition of a set. An alternative definition can be made in the following manner. So for the alternative definition, partition, it's a definition of partition. Definition 1.39 on page 58. Let the set A sub lambda, lambda is a member of curly L be a collection of subsets of the non-empty set A. Then A sub lambda is a partition of A if these things don't work out. Each A sub lambda is non-empty. A is equal to the union of A sub lambda. Lambda goes to F A sub alpha intersect E sub alpha is not equal to 0. That means it's not equal to the intersect. That means they have something in common. Then A equals A sub B. Oh, okay. All right. We're still taking. All right. Let's look at some examples. From the exercises, turn over to page 59. You have the true-false exercises. Those are conceptual exercises. Do true-false. You don't have to pass those in. Just write them in your notebook from now on. All right, but they're helpful because they help you really understand the foundation. They help you really understand the conceptualization of all these different terms and everything. Okay, what you have to do first in the exercises, you're given set A, 1, 3, 5. You want to determine which of the following relations on A or mappings from A to A and justify your answer. Now, we said that a relation is not necessarily a mapper. So you want to think on it for a tree when we do these. Okay, number 2. In each of the following parts, a relation R is defined on the set Z of all integers. Determine in each case whether or not R is reflexive, symmetric, transitive. Justify your answer. So that's what you're given. All right. Number 3. Let R be an equivalent relation defined on Z. Example 2. Write up the equivalence, the elements of the equivalence relation. In practice 2. Okay, so we'll just do 1 or 2 of the examples, and that will pretty much wrap it up.